On to a little bit slightly more difficult practice. It's not real difficult. You just got to remember that if you're rolling without slipping, then you have rotational kinetic energy and translational kinetic energy. Let's see here. We've got a toy car with a hoop of I equals mr squared and a disk 1/2 mr squared and a mass of 2 kilograms. They're released from rest at the top of incline with a height of 3 meters. Height. Whenever I see a height, I think gravitational potential energy. So let's see. mgy, can we do that? M, they all have a mass of 2, so 2 times 10 times 3 is going to be 60 joules of our initial kinetic energy. So we've got that out of the way. And it's going to apply to all 3 of these situations, which we'll use over and over again, it looks like. What is the speed of this object at the bottom of the incline? Toy car. Toy car is just going to go down like normal, or previously. So that means all of our gravitational potential energy is going to be equal to kinetic energy. So it's going to be the 60 joules equals 1/2 mv squared. Multiply by 2, divide by m, or I guess you could remove m from each side if you wanted, and you're going to get square root of 120 divided by 2. Square root of 60. 7.75 meters per second. What is the speed of this object at the bottom of the incline? For this one, we have a hoop that has a moment of inertia, has a rotational inertia. So that means we're going to lose some of that kinetic energy to rotate that object. So we're going to start out with total energy in the beginning equals all of our energies in the end. Translational kinetic plus rotational kinetic. So this is 1/2 mv squared plus 1/2 I omega squared equals 2 mgy. We have I given to us. Let's get I in terms of m. So it's going to be 1/2, and this is a hoop. So let's use the right rotational inertia. Mr squared times omega squared plus 1/2 mv squared. Now we can get rid of that m, make our life a little bit easier. M, and we have r squared times omega squared. We've got a v here, and we're looking for velocity v. We can get omega in terms of v, right? Because we know omega equals v over r. So if it's omega squared, then it's going to be v squared over r squared. I'll stay in the green. So we have, I'm going to move this up here. So we have gy equals 1/2 v squared plus 1/2 r squared times v squared over r squared. Now we have v squared over r squared. Okay. So that means we have an r squared right here and then an r squared in the denominator. So those two will cancel out. And when I rewrite this, I get gy equals 1/2 v squared plus 1/2 v squared, which is just v squared. So gy equals v squared. Square root of that, square root of that. It's just going to be square root of g times y, which I got to be 5.48 meters per second. Try it, check yourself. There was a lot of substitutions there. This is something you are comfortable with or need to be comfortable with at this point in the year. And we're going to do the same process for this one. What is the speed? All of our energies in the beginning, because we have height, so we go right to energies. Translational kinetic and rotational kinetic. So we have mgy equals 1/2 mv squared plus 1/2 I times omega squared. We don't have any kind of omega, so we're going to have to use this relationship up here where omega equals v over r. And because it's omega squared, it's going to be v squared over r squared. And then for the I, this time we're dealing with a disk, so our moment of inertia is 1/2 mr squared. Be careful here because of that extra fraction. Okay, so this is going to be 1/2 times 1/2 mr squared times v squared over r squared. Again, we have r squared in the numerator, r squared denominator. They can go away. And we have m, that can go away, that can go away, that can go away. And what we're left with is gy equals 1/2 v squared plus 1/2 times 1/2 times v squared. Let's move me out of the way. Hopefully that actually worked that time. I gotta be honest with you, I have no idea where I moved myself. I'm sorry. So this becomes gy equals, this is going to be 3/4 v squared, solving for v squared multiplied by 4/3 on each side, and we get v equals 6.32 meters per second. I jumped ahead, but there's your answer so you can check yourself. Now we can go back and we can analyze these energies a little bit more. And we'll start on the left with the toy car. What translational energy does the object have on the bottom of the incline? Well, we know translational kinetic energy equals 1/2 mv squared. We know the mass is 2, so half of 2 is 1, times v squared is 7.75 squared, which, if you remember, is 60. So this is 60 joules right here. This one we've got, again, 1/2 mv squared. M is 2, so half of 2 is going to be 1 times v squared, 5.48 squared, which is 30 joules. 30 joules here. And then over here, 1/2 mv squared, half of m is going to be 1 times 6.32 squared, which was 40 from the previous problem. So we get 40 joules of energy there. Let's see if I can... what did I do? Okay, so how much rotational kinetic energy does the object have at the bottom of the incline? This was just a car moving down, so there's 0 joules there. No 1/2 I omega squared, which is our rotational kinetic energy. 1/2 I times omega squared. What rotational energy does it? So we have... Oh. Yeah, we don't even have to do all that. Sorry, I forgot the situation. Remember, our total energy in the beginning was gravitational potential energy, and then at the end it was our translational kinetic plus our rotational kinetic. If the total was 60, and the translational kinetic we said was 30, then our rotational kinetic energy is going to be 30 joules here. And over here, 1/2 I omega squared, or doing the same thing where 60 in the beginning equals 40 plus k equals 20 joules. Relative translational kinetic energy, all translational kinetic energy for case 1, 50-50 for case 2, and then 67-32 for the last one.